Yes, let me just share my screen. So, yes, my name is Torsten Hoefler. I'm from ETH Zurich, as we just heard. And I hope you can see my full screen now, but I'm pretty sure you can. And I'm very honored to receive this this award. Thank you very much for the introduction, Geoffrey. Thank you very much for the conference and for the opening of the conference. And today I want to talk about scientific benchmarking. And the idea is really to see benchmarking as a science. And the most important piece of this is that in science, what we need is really reproducing our own, reproducing earlier experiments. And so how do we reproduce earlier experiments? Well, we repeat the experiment and we see whether it performs the same, it provides us with exactly the same result. So if it doesn't, it's not reproducible. If it does, it's reproducible, obviously. But what happened in scientific computing is actually quite interesting, in the sense that what the good summary of this is really what Edgar Dijkstra said a while ago. In the good old days, physicists repeated each other's experiments just to be sure, so meaning on different environments. Today, they stick to Fortran so that they can share each other's programs, bugs included. So that is something that I would just like to give you as a little bit of a thinking material. What that means if you're reproducing other scientists' work, if the code is very, very complex. So as I mentioned, reproducibility is the basis of pretty much all of science today. So if we cannot reproduce a result, it is not, cannot be considered scientific. And so let me now briefly define, there is a slight difference between reproducibility and replicability. And in my view, somehow reproducibility is a bit simpler than replicability. And this is all tightly coupled to benchmarking if we talk about performance as a science. And this is what I will get to in a couple of minutes, because we really focus on performance as a science. With that, by the way, do you see this box in the top here? Okay, well, probably not. I apologize. So then the question is really, do we consider reproducibility guaranteed or given in today's environment? So there was a very nice questionnaire in May 2016, whether there is a reproducibility crisis or not. And many scientists, so 1,500 have been asked, and more than 50% agree that there is a significant crisis, and this is a Nature journal, and about 38% there see a slight crisis, and some others don't see much of a crisis, but it's clearly the minority. And if we go a little bit deeper into actually different fields, if you split this now between chemistry, physics and engineering and other, and most of us are probably computer scientists, so high performance computing people, and this is included in the other category. And if you now look at going from, the question was really how much % of published literature is reproducible? How much do you think? Between 0 and 100. Chemistry and physics and engineering are clearly biased towards the 100. So members of these two communities believe that most of the scientific results are reproducible. While in the other category, which includes computer science, as I mentioned, it's more of a mixed, I would say 50-50. So somehow about half, a little bit less than half the community thinks a little bit less than half the papers are reproducible, and a little bit more than half thinks that more than half are reproducible, which is quite interesting because many scientists are concerned, but some scientists in some fields are relatively sure that they can reproduce papers, even though if you ask them more details, like, have you failed to reproduce an experiment in these exact categories that are relatively sure that this is reproducible? Many of them have actually failed. So up to 90% have in chemistry have failed reproducing someone else's experiment. And then the other category is much less, has much less negative experience here. However, it may just be due to the fact that this is not very common to reproduce experiments based on benchmarks. But this is something that exactly that Bench Council and this conference is trying to advocate. And this is why I'm very proud to receive this award. And actually, it really resonates with me, the whole idea of this. So let me go forward and talk a little bit about scientific reproducibility of scientific codes. So I would consider this as relatively simple if we talk about only functional reproducibility, because the idea here is we can just release the code, as Edgar Dijkstra suggested. Of course, this code now includes all the bugs, so we can reproduce it, but we may not be able to replicate the phenomenon, which would mean that we would need to rewrite that code. But again, this is something that is outside the scope of this talk. It gets a little bit more complex if we deal with parallel codes, because now if we share codes that are running multiple processes in our Docker image, for example, and we execute those codes with different numbers of processes because that is now a different machine that we are running on, we may be running into bit reproducibility problems, which are not that simple because IEEE 754 is technically not associative, even if you use a very high precision like double precision. But there are some relatively simple techniques that we summarize in this paper. How do you really build a reproducible application, a bitwise reproducible application that is not really a performance argument, but that's really an output argument, so that the function that this application implements is always the same, regardless on what machine that function runs on. So furthermore, what is most important is that this is actually coming at a relatively low cost. So here we can see that beginning from 1 MPI process up to 16,000, the relative cost is in fact shrinking, and the overhead is relatively small of getting bit reproducible reductions, in this case for MPI. But what if now your main science result is performance? So let me start with one result that I myself was starting as a young student when I was very fresh at Indiana University, as Geoffrey just mentioned here, together with my advisor, Andrew Lumsdaine. And we were working on non-blocking collectives at the time, so that's now nearly 15 years ago. And this was one of my first papers, as I mentioned, so optimizing conjugate gradient solver with non-blocking collective operations. I always found reproducibility very important. This is why in 2006, we published the full code and on our webpage, and so other people could use it and try to reproduce or replicate that experiment. You can see here this plot that we will be talking about in a couple of minutes again. But basically the idea is that we show the difference between blocking collective operations and non-blocking collective operations, and that almost always non-blocking collective operations are slightly faster, and they had some additional benefits in addition to just the speed, but that's not relevant here. But what's relevant here is that we are running this experiment on a domain that is relatively small, because at that time, in 2006, we were running it on a machine that was already pretty old. In fact, it was supposed to be retired that year, so it was already kind of end of life. And we ran it up to 100 nodes, so it was only a 4 GB array. So that's 40 megabytes per node in the largest configuration. What we observed is that in the largest configuration, we found a superlinear speedup. Okay, so that we wrote into this paper. The paper was accepted. It's now reasonably highly cited. I would call this paper a success. So later, successful papers are often, or not so often, but sometimes attempted to be reproduced, and this is great. So some other team, about 1 decade later, attempted to reproduce that work because our code was fully published. So they could just download the code from the web page and rerun it on a different machine now. And now they came to that conclusion that neither the experiment in A nor the one in B could reproduce the results presented in the original paper. And now the question is, what happened? Why could they not reproduce my results from 2006? And I was thinking about this quite a while. I was looking through their results. One of the differences is, of course, the machine. If you use a machine that is 10 years later, where Moore's law had somehow a 100x speed up in between, right? So every 18 months, the performance doubles, especially in parallel computing. You may not be able to get the exact same results. So in fact, it turns out that they could not reproduce the superlinear speed up that we see here, because that 4 GB array was just always fitting into the cache. And that superlinear speedup here resulted from the fact that at 64 CPUs, it did not fit in the cache, but at 96 CPUs, because the relative local domain got smaller as you scale up, it was a strong scaling experiment, then suddenly fit in cache. So there was not possible for them to reproduce that experiment on that new architecture because it was completely different. So what this really means is that reproducing performance results is extremely hard. They would still have, just as a side note, they would still have gotten the exact same calculation result, like the values are the same, but the performance of executing is very, very different because the machines change extremely rapidly. So then I tried to reproduce or replicate several works myself. In fact, this is one of the most successful ones, where we looked at the influence of system noise on large-scale applications in the supercomputing conference. And in fact, what we found is that we could not only replicate results, and many of those are folklore on the system at the time. The largest system on the planet was Jaguar. So Kurt Ferreira, Patrick Bridges, Ron Brightwell, and Pete Beckman, they were all independently publishing various results related to this machine, that it basically stopped scaling at about 15,000 processes, which was very shocking because it was a leadership class machine and it should run more than, it had more than 15,000 processes, but you couldn't really run larger applications on that machine. And the question was why? And we've been able to explain that by replicating these results and adding a theory to it that was explaining all these results. So for that, we actually got the SC 10 best paper, because really, even in the community, replication and reproducibility is very well regarded. So this is just something to motivate you to replicate other works. And it's very pleasing to see that at this conference that we are at, the 2 best papers are also the 2 best papers in terms of replication results. So this is very, very encouraging. So really, replicating performance results is possible, but we should make it the default because it's too rare today. So the question is now, is it worth trying in the high performance computing community? Because as I mentioned, performance is very, very quickly changing from generation to generation of machines. And now we could go into a very small quiz, which if I would have given that talk live, I would have asked you in the audience, do you believe that you could reproduce, or somebody could reproduce any Gordon Bell finalist from before 2015? So just 5 years in the past. And usually, if you now think about this for a while, well, these Gordon Bell results, these are the largest, are running on the largest machines, are running the largest applications, the most challenging applications. So could we reproduce those 5 years later? Well, most likely not, because these machines are probably not in existence anymore, or even if they still exist, they would be running a completely different software and system software stack that completely changes the performance. So at least at the very high end of the high performance computing machines, we will not be able to see or we will not be able to reproduce these results one-to-one. And this is why I want to advocate a different measure that could replace reproducibility. And that goes a little bit beyond, it's also more complicated, but this is our only chance, I think, which is interpretability. So here we call an experiment interpretable if it provides enough information to allow scientists to understand the experiment, draw own conclusions, assess their certainty, and possibly generalize the results. Right? So we do not only bank on reproducibility, which is incredibly important, but we also want to make scientists understand the results. And this is something that is it's quite interesting. And I want to make this talk a little bit lighter by introducing one and later a second plush character, which I call Garth. And this is now, Garth stands for the young, inexperienced, but extremely smart students. So we all have many of those if you're professors. But the question is now, how do we make high performance computing a science? And especially when measuring performance, if you are now Garth, the young student, and I'm sure even if you're more senior, you have been that student at the time. I was it at around 2006. So the questions you have to answer is, how many iterations do I have to run per measurement? How many measurements do I run? How do I summarize the data? How do I compare performance in different systems? And how do I even measure time in a parallel system? Because all these CPUs run at potentially different times, at potentially different speeds even. So that is not so simple. So the big question is now, how are these questions answered in the field today? And by the way, there are many, many more. And typically what you do is, you're a young scientist, you ask your advisor, and your advisor typically comes up with some kind of intuition that says, well, measure it 1,000 times, or measure it 100 times, or measure it until the variance is small or something. But this is exactly where the problem lies, because if we now have different standards for these things based on intuition of different people, then the community will not agree on scientific principles for benchmarking. So now the question is, do we already have these scientific principles for benchmarking, or do we still need to establish them? So if you look at the state of the practice in high performance computing, and we did this in a rigorous way, but we looked at a stratified random sample of 3 top conferences, HPDC, PPOP, and supercomputing, and 4 consecutive years of these conferences, and we are drawing 10 random papers for each, which is about 10 to 50% of the population. So we got 120 total papers, of which 25 did not work on performance, so that's fine, we excluded them. And then we came up with this very large table, which I don't want to explain in too much detail. It's also anonymized because there is a very high variance across the different conferences, and I didn't want to point out which is the not so good conference. But if you look at this table, and you can find them in the paper that I'm going to cite if you want to see this in greater detail, the main result is really that most papers represent lots of details about the hardware, but don't describe the software environment. And as we all know, software can be as critical for performance as hardware. The tool chain, the stack, everything will change my performance. And if I only have half of the picture, I may not be able to reproduce. Furthermore, many of the papers are not explaining their measurements well and are thus really easy to question unless I have access to exactly the same machine. Furthermore, unfortunately, there is no statistically significant evidence for improvement over the years because we sampled from 2011 to 2014. So now the big question is, well, did it improve until now? Because that's, after all, 6 years ago. And the fortunate answer is, I have the feeling that yes, we are getting better as a community, but we still need to pick up speed. And then the main thesis based on the survey is that performance is often impossible to reproduce. So this is why we really just need to present enough insight, and this is especially true for the Gordon Bell Award, which my team was fortunately winning last year. But it's really, really hard to make this reproducible because we were running on the Summit machine at full scale, and of course, not everybody gets the privilege to do this. Even though we publish all our code and all our results, it's going to be very hard to reproduce this. By the way, in the meantime, the Summit machine has updated their firmware and their runtime software, so this is all very different as of now. So we all know about this, but how do we fix this? Well, actually, this is a long-running discussion that we are having. So nearly 30 years back, there was this very famous paper, 12 Ways to Fool the Masses when Giving Performance Results in Parallel Computers. This was continued with various other papers that were basically all complaining, for example, how did this get published, about the state of the art in performance measurement and performance analysis. So what we try to do is slightly different. Instead of having a destructive approach and complaining on how to not do it or giving negative examples, we want to give positive examples. And inspired by the 12 ways to fool the masses, we want to provide 12 rules to inform the masses to make benchmarking better grounded and better or closer to a real performance science. Of course, this set of 12 is not complete like any limited set in a complex field, but what I want to do is I want to quickly illustrate these 12 rules now, and I want to use Garth and Eddie. By the way, Eddie is the advisor of the young student, the eggplant down here, that will basically ask the hard questions. And in case you're a professor, please take this to you and ask these hard questions to your student. So for example, the first one, I can make fun of myself in the sense when I was a young student. I produced this plot, and this is fully my fault, but this plot is a speed up plot. So you see here the number of CPUs from 8 to 96, and the speed up from 0 to 100, and we get nearly linear speed up. In fact, a little bit of super linear speed up, so we get a little bit higher than 100 than at 96 CPUs. So this is all great. I swear this was measured correctly. However, we cannot tell from this diagram whether this is a good baseline or not, whether the code that I ran on a single core or on these 8 cores here as a baseline was actually fast or it was really, really slow. And this is a common pattern that repeats that was seen in 1988. This is included in Bailey's 12 ways. In fact, 38% of the papers that we looked at that reported speed up did not give us the base case performance. So even 5 years ago, it was not that uncommon to not provide baselines. And people were complaining about this in different communities as well. This is more one of the funnier papers of Frank McSherry's Scalability, but at what cost, where he basically shows that he can beat various clusters in the AWS cloud at the time with his Hello Kitty laptop running graph processing workloads, because those are incredibly hard to parallelize, but people are still running them in parallel, even at a loss. So this gets us to rule number 1 that I want to formalize, is when publishing parallel speedup, report the base case as a single parallel process. So this is really simple, or the best parallel execution, as well as absolute performance. So a very simple generalization of this rule implies really that one should never report ratios without absolute values. Very simple. So now let's get to a second example where our student Garth wrote a new compiler and looks at the NAS parallel benchmarks, a very well-known benchmark suite. So we see speed up versus ICC and LLVM. Here are the two ICC and LLVM, and now the new GarphCC. The higher, the better. So we see in all these 3 examples, the gray bar is higher than both other bars. And this is actually a real result. So these are real measurements. So this is not made up. And we see that this is all better. But now the question is, well, what happens for FT and BT, which is also part of this benchmark suite? Again, we're at a conference called Bench, so we really care about benchmark suites. So it turns out that GarphCC did not work for FT, unfortunately. And it was 20% slower for BT, and Garth thought that doesn't really make his point, so he should not present these results. And of course, you must present these results even if they don't make your point in your compiler is worse for specific results. So very simple rule number 2, specify the reason for only reporting subsets of standard benchmarks if you're not using all system resources or all benchmarks. So very important is that show your results even if your code stops scaling. And this is very, very important piece. So even if you have a machine that has 10,000 processors and your code stops scaling at 2,000, you should run experiments way beyond your scalability line to just demonstrate where it stops. Furthermore, now the interesting question is, well, okay, let's add the BT benchmark, and it's in fact 20% slower, as I mentioned before. Great, so we still have these 4 benchmarks. But now we could argue that 20% plus 20% plus 20% minus 20%, the average of those is 10%. And so you could still argue that GraphCC across all of those is 10% faster. But of course, many of you have probably captured what I did wrong, because I shall not use the arithmetic mean for ratios. Very important. So what I can do is I can use the geometric mean, and then I receive an 8% speed up over those. But the geometric mean is better than the arithmetic mean, but it's still not perfect because it's actually quite hard to explain what it does. And we can discuss about this in Slack, but that is something that is actually quite complex because the geometric mean has no clear interpretation. But if you look at the total completion time of these workloads, we get a completely different result because BT runs much longer than the other benchmarks. And then GraphCC is, unfortunately, if you look at the completion time of the whole benchmark suite, about 10% slower and not 10% faster, or 8% faster as suggested by the geometric mean. So that gets us to rule number 3 and 4. And these are a little bit more complex than the previous ones. So the arithmetic mean is only for summarizing costs that have a direct relationship with what we understand, so a linear relationship. If we talk about rates, we should use the harmonic mean. Furthermore, ratios, like the one I showed before, the 20% speed up here, they should really never be summarized unless it's absolutely necessary. We should really use the base, the rates that the ratio is based on instead. And this is quite complex. So out of the 95 papers that we reviewed, 51 papers use some form of mean, but only 4 specify which mean. So the default is probably the arithmetic mean, which is quite bad. A single paper correctly uses the harmonic mean, which is great, out of 95. 2 use the geometric mean, but without any reason. And there is also a huge community in other communities. So the only strict thing we can say actually about these means is the relation that the harmonic mean is smaller than the geometric mean, or equal is smaller equal than the arithmetic mean for any set of numbers. So that is really the only mathematical explanation we have here. So, but now let's get a little bit more complex to benchmarking network latencies on a cluster system. So now we're talking about ping pong latency, so no compiler anymore. And the advisor Eddie asked his student Garth to benchmark the latency on a specific cluster. That's the Pittstora system in Switzerland. And these are, again, real measurement values that were collected on that particular system. And Garth says we get 1.77 microsecond. By the way, the Pittstora system is a Cray-Shasta Cray-Shasta system based on the Arias network architecture. So now the question is, how do we get this? Well, Garth ran 1 million tests and averaged across these 1 million tests and strongly believes that the result must be right. Okay, so, but now what we could also do is we could look at each of those tests in isolation. So we could plot 1 million points. Here are the samples from 0 to 1 million. And we could plot the observed time for each of those if we just measure them separately with high precision timers. So this is what we did in this case. And we can see that most of those values are around 1.77 microsecond here, and probably because we don't see it due to the scale. But some of those are more than 800 times slower and are actually above a millisecond. So, and there's some distribution here of these different values, and I will explain where this comes from in a couple of minutes, but we observe that there's actually a distribution. So now the question is, if you present a single number, like this 1.77, I do not see that distribution. I do not know whether that is close or not to the actual expected values or to the probability distribution we are drawing the values from when we are measuring. So really, most papers report non-deterministic measurement results because performance is almost always non-deterministic. If I'm running a benchmark twice, I will get similar but not the same performance. And of those 150 papers, of those 95 papers, only 15 mention some measure of variance. And unfortunately, only 2 report confidence intervals And both of them use, in my opinion, the wrong confidence interval, unfortunately. So nobody really uses the real confidence interval. But confidence intervals are incredibly important, and we will talk about this in a couple of minutes. There are different forms of confidence intervals that we should report for specific distributions of benchmarking data. So, by the way, talking about non-deterministic data can be very, very simple. So you don't really need to plot all these million results every single time, or you don't need to plot any error bars or something. You can just add sentences like this, of course, verify them before we collected measurements until the 99% confidence interval was within 5% of our reported means, because then I'm happy. Then I understand, okay, the distribution is not very wide. I have a relatively high confidence that this is correct. If I just say the mean was 1.77 microseconds, this can be arbitrarily wrong, if you see in a couple of minutes, for that particular result. So now Garth, actually he's a clever student, as I mentioned, so he opened his textbook and said, well, let's compute the confidence interval, which is now between 1.765 and 1.775 microseconds for the actual data I showed you. And then, great, this is very, very tight, because 1.77 was the actual mean. But now the question is, did you assume normality of the data? So did you assume the data is following a normal distribution? Well, of course, Garth is clever. So he followed the central limit theorem and normalized the data by subset summing of size 100. But let's actually look at the data. This is now, again, the same data that I showed you on the previous slide, just arranged in the density plot. Here is now the microsecond time going from about 1 to about 6. And if I'm drawing this data here, you don't see much, but what we can do is we can draw a QQ plot, a quantile plot, that tells us about how normal the specific data is if it lies on a line, and you can on a straight line. You can clearly see this does not lie on a straight line because there's this bump here. Even if you log normalize the data, it doesn't get much better. If you subsum the data with blocks of 100, like Garth did at the beginning, you get slightly closer to a normal distribution because the central limit theorem holds. If you subsum the data with 1,000 elements, so you take your 1 million elements and reduce, add blocks of 1,000, you will get closer to a normal distribution, but still it's not quite a normal distribution. So we will see in a couple of minutes how the distribution actually looks like, which is very, very interesting. So it turns out that the data is not normally distributed at all. And the real confidence interval is somewhere between 1.6 microseconds to 1.9 microseconds. And this is actually quite wide open if we were about 1.77. That is about a 10% deviation in both directions. So that's quite bad. So we should really not assume normality of the collected data. For example, some textbooks suggest that if you take enough samples, the data will be normally distributed, which is actually completely wrong for most of performance critical results, because you almost always have heavy right-tailed distributions, because typically computers get slower and not faster when you have deviation. So typically your computer is slowed down by noise and is not sped up by noise. While in a normal distributed system, you would have the same probability for getting faster or getting slower, which is not really true in computers. Also, the central limit theorem is of course correct, but it only applies asymptotically for an infinite large number of subsumming or sampling, which we of course cannot afford. So these two papers that I mentioned, unfortunately, they used the wrong confidence interval because we don't know whether the data they based it on was normal or not. And it's most likely not normal on my discussion I just had. So now the question is, what do we do with not normally distributed data? And this is quite interesting as well, because there are lots of rank-based measures where we make no assumption about the distribution, sometimes also called non-parametric statistics. For example, the well-known median, where we sort the data and just take the middle of the sorted data, so it's sometimes also called the 50th percentile, is much better than the mean. So for example, if we look at this plot here, which is now high-performance LINPACK runs on the particular architecture at the Swiss National Supercomputing Center, where the completion time varies between a little bit less than 280 seconds and a little bit less than 240 seconds. And here is the density plot, and here are these bar plots are the actual observed measurement results out of a series of 1,000 measurement results. So the green one is the minimum. This is what we would report for the top 500 list. The light blue one here is the median, which is actually where most of these measurements lie. So it's very, very close. It has a reasonable 99% non-parametric confidence interval, and the arithmetic mean is lower than that because it's now affected by the long tail, which we can characterize by the 95th quantile or by the max itself. So this is how we can do data science on performance results or on benchmark performance results. And percentiles like the 25th and the 75th are incredibly useful in practice to tell us something about the distribution. Because if I only tell you the minimum value, then of course I know the performance not to be exceeded on that system, but I still know absolutely nothing about the expected performance, which is more about 5 teraflops per second less for that relatively small compute system here. Okay, so now the question is, how do we compare non-deterministic measurements? So really, Garth has seen some variants using GarfCC as well. This is now the compiler we mentioned in a couple of slides earlier. Now the question is, how much variance did we observe? Because I just showed you the 20% speed up or 20% slowdown. And now if we look at this 20% difference here, at the actual measurement results, again, this was compiled with a real compiler, measured on a real system, ICC versus GarfCC is a changed version of GCC, by the way. So we had the 20% difference in the median, but unfortunately, the 95% confidence intervals in this particular data is actually overlapping. So really, this is statistically seen no evidence of a huge difference between because the confidence intervals overlap. So this paper should not be published. Unfortunately, it was not published. It was just an experiment for our talk here. So really what is incredibly important, if we have non-deterministic data, we need to compare that data. We need to compare not only the median or the mean, but we really need to compare it using statistically sound techniques, for example, confidence intervals or analysis of variance techniques. So, by the way, many of those techniques that I mentioned here are quite involved. And if you want to learn more about those, you can read the paper that is cited at the bottom of some of those slides, like this one here. Okay, so now let's go back to the ping pong data, and let's look a little bit closer into the actual distribution. So here I'm zooming in that exact same data that I showed you before. I showed it to you in the scatter plot. I showed it to you in the QQ plot. I showed it to you in the density plot. And now I'm going back to the density plot, and I'm zooming into the area between 1.5 and 2.2 microseconds latency. What we see here is quite interesting. We actually see the probability distribution of observing certain values. And now, if we look at the arithmetic mean, it is in an area, this is the 1.77 microseconds that we heard before, it's in an area that is actually really not observed in practice when we measure that system, because we observe this mostly and these two humps here. Furthermore, the 99% confidence interval based on the normality assumption is incredibly tight. So this is the wrongest result you could report. This is actually quite important that if you report this on this machine, you report a number that you will never see in practice, and you will report a very high confidence interval. So you do two things wrong, even though you may be thinking you're doing it right. If you go for the median, as I suggested, for non-parametric statistics, what you will see is already slightly better, because you see that the 99% confidence interval, now the non-parametric confidence interval around the median, is much wider. It actually has a variance of more than 10%. And you will, if you continue measuring, you will not reduce that variance here, or that width of the confidence interval, which means there is something wrong. And then you look at the distribution, and then you find out, oh, I have two modes here, mode number 1 at around 1.65 and mode number 2 at around 1.95. What are these two modes? Let me look at the system itself. As I mentioned, it's a gray area-based system. If we have a source and a destination, so this is now the network topology here, that are connected nearly fully. So I have a source and a destination node. The machine now has two different ways to transport that message from source to destination. One is it sends it directly. Then we are ending up in this mode. But there is a second mode, because the machine uses adaptive routing, where it sends it to some other router that then sends it to the destination, which is a slightly higher latency. Of course, it gives you a higher bandwidth at the end, but for latency measurements, this is important. So we are ending up in this area. So really, it's physically impossible to observe the arithmetic mean on this particular machine, because it's bigger than the direct connection and smaller than the indirect connection, so it cannot happen, but we would still report it, right? So remember, this is can be quite bad. Now, if you look at a different machine here, this is the Pilatus machine. It's an InfiniBand-based machine. It does not use adaptive routing. It really routes every message along one route. And here we have the distribution, which is now looks nearly like normal. I mean, it's easy to normalize. The median, the confidence interval about the median is sufficiently small, so we can immediately stop measuring here and don't even need to look at this. The arithmetic mean is very close in this case, but this is just by chance, as I mentioned. So now the big question is, if you ask me which of those two machines is better in terms of latency, this machine or this machine? And now it gets tricky because, of course, this machine, many of the messages are faster than here, but also many of the messages are slower than here. So now we need maybe a slightly different way, a slightly more differentiated measure of understanding the performance of these machines to compare those. And this is where a really heavy weapon you can roll in. This is called quantile regression, where you compare each of the quantiles of these distributions. And for these two machines, as we compare them, I don't want to go into too much detail because I don't have enough time, we can summarize the results of quantile regression that Pilatus is better for worst case latency critical workloads. So if I care about the worst case latency or the 95th percentile, 99th percentile, then Pilatus is better. But the DORA system, the top system here, is on expectation better because the median is slightly better, as you can see here. Right? So you may actually want to differentiate more. And in the data center environment, this is very, very, very crucial. Probably the lower system, Pilatus system, would be preferred because tail latency is incredibly important there. So rule number 8 is tricky, but very important. You need to first, before you use a single measure of central tendency, you first need to understand whether that is useful to use. So there's actually a paper in the SIG-Arch Computer Architecture News, why you should care about quantile regression, discussing this in greater detail and pointing out that some results reported in papers at scientific top conferences are actually incorrectly interpreted because of these statistical problems. Right? So we need to be very careful here. So now to a very practical way to benchmark. How many measurements do we need in order to benchmark my system? And as I mentioned, very often this is based on some kind of intuition. But as we now learned, we should use the confidence interval to do this. So really, we should measure until the 95% confidence interval is within 5% of the mean or something like that. So you can pick 99 and 1%, or you can pick some percentages as you like, but at least we now know how to interpret this. If you will not be able to move the 99, some high percentage confidence interval within some low percentage of the mean, then this indicates that you have some problem in the distribution and in your system, and then you should look at the scatter plot. Right? This is actually extremely helpful because it can even debug performance issues in your system. But now, the problem, what if you cannot afford more than a single measurement? I mentioned this with the Gordon-Bell run. We cannot afford to rerun that experiment, which is actually problematic. However, many codes have a very repetitive nature. And what we did for that particular run, we've been able to look at the phases of the code, which were run many thousand times during the execution, and measure them individually and not just the whole code. And then we could gather statistics across the phases, and we found that the machine was actually very well behaved. So Summit is a very nice machine in that particular environment. So now let me get to the next point. Now we say, okay, let's move to something else. We are now measuring MPI reduce. And MPI reduce, if we run it with powers of 2, so 2, 4, 8, 16, 32, and 64 processes, behaves much simpler than before, because now the distribution here plotted as a box plot is very, very narrow. So great. But now the question is, well, did you design that experiment well? Did you try other numbers of processes? Because powers of 4 is often optimized. So if we now use powers of 4 plus 1, we get a completely different performance curve and actually a slightly higher variation even in the low end. So rule number 9 is a little bit more complex to understand because we need to document all varying factors, where we recommend factorial design, and you need to talk about all the parameters you choose. So this is just common sense, I would say, but you need to be very careful when picking those. Now, more complex is now the time in parallel systems, as I mentioned, super hard to measure. So for example, Garth, a little bit naive student said he develops a broadcast that takes only one latency, like so one point-to-point latency to finish, which is of course theoretically impossible. But I measured it, so it must be true. Look at this benchmark code. This is extracted from the Intel parallel benchmarks, or the formerly IMB benchmark suite. This is the loop where I'm just taking the time, I run 1000 MPI broadcasts, and then I take the time and then I divide the time by 1000. Now imagine this very simple broadcast implementation where every process I sends the message to I plus 1. 0 sends to 1, sends to 2, sends to 3, sends to 4, sends to 5. After 0 has sent its first message, it can immediately start the second broadcast and send the second message, and so on. So you see that these messages are, in fact, these broadcasts are pipelined through that network, and they finish now with the difference of 1 latency. And if we run 1000 of those, the pipeline startup overhead will be negligibly small, and we will actually measure, in fact, a single latency. Completely wrong. So we need to measure each operation separately. Very important. Furthermore, if I now run a reduce, and I look at the detailed data, if I now measure each operation separately, but now if I look at the different processes here, process 0 until process 63 out of these 64 processes, we see that there is a very highly variance across the processes. While process 64 takes about 30 microseconds to complete, process 63, process 0 takes more than 60 microseconds to complete, right? So rule number 10, for parallel time measurements, we need to report all measurements in the optional synchronization and summarization technique. This is extremely complex and there's no general rule. So this is, again, a bunch of hints for you to understand how to do this. Measure events separately, use high precision timers, synchronize processes. And again, how to do this in practice is all explained in that paper that I cite down here that you can read at home. Furthermore, what does time mean? And this is, or what does performance mean? It's very often hard to interpret. So for example, if you tell me that I can compute the 10 to the 10 digit of pi in 2 milliseconds on that DORA system, I have no idea if that system is fast or if the code is good or not. So really hard to understand. So what would be really good is if we can provide the ideal speedup, the undialed speedup, and parallel overheads. So if we now take this apart, we could look at the time. These measurement results are here, the red triangles, what we're actually measuring. The green is the ideal linear bound. So if you just scale the code from 17 milliseconds on a single core to, I don't know, 17 divided by 32 milliseconds on 32 cores. Then if we consider Amdahl's law, we can draw the serial overheads bound. And actually, if we consider the time of the reduction that it costs, we get to this this parallel overheads bound. And we can now see that the code is actually performing quite close to these bounds. We can also plot this as a speedup plot. So this was a time plot. This is exactly the same data as a speedup plot. Remember, if you plot speedup plots, we should have always the serial base case. But we can now see that this code is actually well optimized and runs relatively well. So as the rule 11, and this is one of the most powerful rules, if you show upper performance bound, you can facilitate interpretability of the results, and even better, you can prove sometimes that your implementation is optimal. Furthermore, and the last rule is very, very simple, plot as much information as you have. So use box plots, as I have showed multiple times in this talk. Use violin plots. I haven't shown those in the talk, but they show you the actual distribution. As you can see here, this is again our result that I showed you earlier, the actual distribution of the data. Or you can even show box and violin plots combined, even though that may become a little bit messy. But there are really easy plotting tools for this particular purpose. So rule number 12, plot as much information as needed to interpret the experimental results. So wrapping up the rules and coming to an end of the talk, so we really want to emphasize interpretability of performance experiments. These rules are mostly to teach young scientists, but also experienced scientists, and you can find more explanation in this paper and actually real recipes how to benchmark. And this matches very well the Nature 2016 questionnaire, where the question was, what factors could boost reproducibility? And one of those was better understanding of statistics. So this is really half of the talk was better understanding of statistics and better mentoring, supervision, and more robust design, and also better teaching. So I'm actually also teaching these results now, or these benchmarking strategies, which is very important, I believe. So with that, I would end with a call for action. A performance may not be reproducible, but at least we should focus on interpretability. This enables us to build on these results, and we need to foster this interpretability. Maybe even enforce this in technical program committees. I would see these 12 rules as a start. They need to be extended or made more concrete. We started this by implementing many of them in libscibench, which is a library for scientific benchmarking that you can use for reproducibility purposes. I want to close with one last word before we go to the questions. I have another 12 rules, 12 ways to fool the masses when reporting performance of deep learning workloads. So this is really a humorous guide in the New York Times if you look at deep learning and other experiments. So thank you very much.